How do you want to start this?
Just tell me, what should we look at today? My mind's gone blank and I can't remember the last point we got to with our little robot inside the CPU or CPU
Right.
robots.
So why don't I start by recapping our story so far? I've been using this somewhat slightly cutesy idea of a conveyor belt with robots working on the conveyor belt to explain the processes that go on inside a modern CPU. We have our conveyor belt. On the one end, we've got a robot, and I forgot how I draw robots now, something like this. And that robot is picking up instructions that need to be executed and shoveling them on as fast as he can onto the front of the conveyor belt here. And those instructions, those are just numbers that are written down in boxes in memory, which we've talked about before. And those numbers encode the work that the organization, the CPU as a whole, is going to do. Those numbers need to be interpreted somewhere. So along this conveyor belt, there is another robot that's going to sort of decode those sequences of numbers and say, oh, this means I should add 300 to 750. Towards the end of this, there's an array of robots in a modern CPU. There's like a half dozen of them, in fact, each of which has their own abacus, which I've forgotten how I draw. There we are. This is how we drew an abacus last time. Look, I can draw, right? Something like that. Each of these is capable of doing a mathematical operation that might take a little while, like multiplying or division, right? In the last video that we talked about, we sort of had this process by which we had like a scoreboard at the end of the conveyor belt, and we'd written down lots of information about which pieces of work needed to be done, and critically, what pieces of work those depended on first. So if we needed to multiply a number with another number, and then we needed to divide the result of that by 7, the person who was going to do the divide had to wait until the multiplication had been done. But if there was some addition to be done that was independent, we could do that separately, which is why we could have a half dozen robots at the end, each of which doing independent calculations, all of which came from one stream of instructions. Most of the time, modern CPUs are aiming for 3 to 5 instructions per clock cycle, IPC is called, where in any one tick of the clock, at least 3 things are finishing being done, which is amazing. And this is we're not talking about the number of CPUs that you've got, like, you know, if you look inside Windows settings and you see you've got 16 CPUs. I'm not saying those are the 16 things they're doing. Each of those 16 CPUs could be doing 3 or 4 or 5 things every tick of the clock. So it's pretty clever. And I went through an example last time. I've actually got the sheet of paper here. I found it, where we sort of wrote out this equation and we determined that if we gave a name to each of these individual parts, like T1 is this x minus x2 here, we could see that this subtraction of x1 minus x2 could happen at the same time as this subtraction of the y1 minus y2. And so there were 2 pieces of work that could be done at once. And I showed it with my little whiteboard how the algorithm worked. But I glossed over these T1, T2, T3, T4, T5 because I just made those up. I just wrote them down because it made a convenient way of expressing it here. But if we go back to our original way of expressing the code to the computer, let's do something super simple. So I'm going to make up something very, very straightforward that can demonstrate the point, and then we'll sort of talk about how it's not exactly like that, which is, you know, how these things go. So I'm going to pretend that somehow the 6502 that we started with, where has an instruction called LDA, load A, and I'm going to say load from memory address 100, this means. So read into our little accumulator register whatever's in memory address 100. Then I want to multiply it with itself. Now, the 6502 didn't have a multiply, but I'm making up a multiply here so that we've got a long piece of work to do. And then I'm going to store it in address 100. So what I'm effectively doing is I'm reading a box, I'm squaring it, and I'm putting it back in that box. You can also imagine you want to do that to box 101. So we're going to start with that. And I'm just going to try and keep this as simple as possible because it gets very complicated quite quickly. So we're going to store in 101. Okay, so here we've got a fairly typical snippet of a program that wanted to square something that's in box 100 and square something that was in box 101. Now, if I were to draw out my scoreboardy thing, there would only be one piece of work that we could do here, because if we look at each instruction in turn, we can see what it needs before it can start. So this load instruction at the beginning can start immediately. It doesn't depend on anything. We know that we just want to read the contents of box 100 and put it in the accumulator. So that can go straight away. Okay, great. Multiplying A, well, I need to have read A before I can multiply with A. So this needs the previous thing to finish. I'm going to put a little arrow here to say this depends on the result of the previous instruction. Similarly, we can't store the result until we've done the multiply, so this depends on the previous instruction. Now, we're back to a new load A with 101. Now, ideally, we would like to start this as well. We could see that, like, from a human point of view, you could square box 100 and square box 101 at the same time if you've got two abacuses, right? But we can't load into the A register here because it's being used by the other robot that's squaring the first number, right? We can't write to that A register. So, if we were programmers, we could maybe make up a B register and then a C register and then a D register. And then eventually you're going to run out of register names and you're going to be like, well, I don't know what we're going to do here. But from a very practical point of view, the computer exposes only a couple of these registers to the programmer. And in the case of the 6502, it only really has that A register, the X register, the Y register, whatever. So we can't start this LDA until the previous thing has finished, and then we can sort of follow this through. And essentially, although we might have 2 or even 3 robots with abacuses, only one of them is going to have anything to do because of this chain of dependencies. So luckily, there is a trick, and there's a trick coming, which is to say, this A register here, if it was cheap for us to have lots of them, we could get a robot at the end of our pipeline. So just before it gets written onto the scoreboard, we're going to have one last of the robots that needs a name. I can't think what we were going to call him, but this step in a pipeline is called register renaming. And he has a little chart, and it says that when somebody says A, what they really mean is slot X. And slot X is in this chart. And I'll draw it out in a second, and hopefully it'll make sense a little bit more than me describing it there. But effectively, he's going to rewrite all of these instructions as they go through in terms of slots inside the table where all of the work is being stored instead of the A register anymore. And we're going to forget that the A register even exists, except for right at the very end, actually. So the sort of the classical pipeline is we have this long sequence of events that happens. It ends in this sort of register renaming step. And now there's this big sort of melee of robots just doing as much work as they possibly can. And at the very end, we have something called retirement, where the instructions are finally written out, and that happens in the order that the program wrote them in, regardless of how quickly or otherwise they were done by the robots in between. And there we need to know that it was A again. But in the middle bit, we don't care. We just use this slot number. So I'm going to take my little piece of code over here, and I'm going to pull out my little whiteboard thing that we used before. And I'm going to use this post-it note, because as we know, all computers run on whiteboards and post-it notes. And I'll try and get the glare not to reflect too badly. I'm sorry about that. And so this is just going to remind me where the A register currently is, so that if I see an instruction that says, hey, I need the A register, I'm going to remember which slot it's in. And these slots are these slots here, 0, 1, 2, 3, 4, 5. We've got 6. Sorry, I counted at 0 because I'm a programmer. So if you get to 5 and you're a programmer, there are 6 actual slots, off by 1 problems that happen everywhere. Now, although it's a whiteboard, I'm going to use my Sharpie because my whiteboard marker has run out, so I can't make any mistakes on this one. Otherwise, I need to go and get some rubbing alcohol. So our pipeline takes our registers and says, load A with 100. Now, at this point, it doesn't matter where the A register is because I'm about to replace the contents of the A register with something completely different. So when we take our load A with 100, I'm going to say the output of this stage is the A register. The operation is load. The input one is address 100. And I'm going to say, okay, this is where the current A register is. So I'm going to put a little marker on here that says, if somebody else says A, what they really mean is the result of slot 0. So then let's go to our mul. Mul A, well, this is going to output to A, and it's a multiply, and its input is A. Well, the input to A is actually slot 0. So whatever comes out of slot 0 when it's finished doing its computation is going to go into the input now. And I don't have to remember that this is A. I mean, I know that it's A where the result's going to go, but also because I'm writing to A, now anyone else who cares about A is going to go here for A, right? Then we've got a store. Store doesn't really have an output in terms of registers, so I'm not going to write anything here. It is a store, and input 1 is the A register. We're going to store the A register in location 100. But again, the A register is actually whatever came out of slot 1. 1, and it's address 100. And then the A register is still over here. If we needed to read from the A register again, we would always read from slot 1. But we don't. We're going to write back over the A register. It doesn't matter what the A register was, because in this case, load A with 101, A load 101, and now A is down here. And you can see that we would finish off the rest of these here. We'd have another multiply here, we'd have our store here, and this multiply would be slot 3, and the output of A would go here. This is A, and this last one would be store whatever came out of slot 4 in address 101. And so we no longer have that weird dependency, that problem where the A register was going to be read to and written from by two independent robots. So if we were now to look at this new version of the code, not this one that's over here, this first slot doesn't have any dependencies, so it's ready to be run. Any robot could pick up this work immediately and do this read into slot 0. This one we can't do because it needs slot 0, and slot 0 isn't complete. This one needs slot 1, and slot 1 isn't complete. This one, this one could be done. This instruction now can be used because it has no dependencies other than somebody being able to read into it from memory address 101, and then this one similarly is waiting and waiting. So now we've got two independent pieces of work. Two robots can pick this up at once. They're both going to go off, read into memory. They're going to come back with a number. Let's say the first robot gets back the number 9. So his answer is 9. And so when he completes, he says, I'm slot 0 and I'm the value 9. And immediately any of the other remaining slot 0s can be replaced with the value 9 and they become ready to run. But that, of course, doesn't invalidate anything that's happening in the second half of the instructions. These three instructions are independent of that now. Whereas if we just said the A register, we'd have been confused. So in this way, we have designed away the problem of two independent streams of logical operations that happen to use this A register. We've now teased them apart and we can run them in parallel. And even with things like modern CPUs where you have more than just the one register like the 6502 has, it's still a real problem. So register renaming is a really important thing. So just to give us an example, the modern x86 has 16 general purpose registers. So you'd think this problem would happen 16 times less. But internally, it has somewhere in the region of 280 of these slots, which means it can do 280 independent pieces of work, even when on paper you'd have to be very careful about using different registers for the work that you're writing. Another important part about this, and the way that I unfortunately is a little hard to do with only 6 slots on my piece of paper, or without getting it so complicated we end up drawing a huge picture, is, I'm going to throw it over here, is typically this kind of thing happens when you have a loop. So the way that you would probably have written this bit of code here is you wouldn't have written it out as load 100 and then load 101. You'd have written something like, here's my loop, load A with 100 index by X, multiply A, store A, 100 index by X. So it's a bit like our original example where we were doing Fibonacci numbers. Then I'm going to increment X, and I'm going to compare X to, I don't know, 1,000 to say, we're only going to do 1,000. And if it's not equal to 1,000, I'm going to go back to the loop. And so this is a very convenient way of writing out maybe 1,000 multiplies, a square 1,000 different things in 1,000 different boxes. And of course, we're forced to have to use the same register over and over again. Otherwise, it wouldn't be a loop. I'd have to write it out 1,000 times. And I'd have to use 1,000 different registers, or I'd have to use as few registers as as many registers as I could to try and prevent this renaming problem. And the real key observation is how this all comes together is that the pipeline that's going to do this loop, the branch predictor, which we spoke about before, has essentially taken this loop and it's stacked them one after another by predicting that that's the way the instruction is going to go. And so the pipeline is flowing along with just multiple copies of the same fragment of code over and over and over and over again. And so because it's copies of the same code, it has to be the same register, which would mean that you would have to do this renaming in order to actually get some of these multiple flows going at the same time. And what it also means is that in modern processors, a loop like this, if it can be predicted well, it's actually multiple versions of that loop could be running in parallel. That is, if it's fast enough, if this multiply takes, say, 10 cycles, it's possible for the branch predictor to have gotten around the loop several times before the first multiply completes, which means that the second multiply is starting and the third multiply is starting and so on. And so you get this huge speed up from being able to get multiple pieces of work started at the same time. Now, when it comes to retirement at the very, very end, so we did talk about this briefly before, retirement happens in order again. So even though when we were sort of describing this particular situation, instructions 0 and 3 would run together, instructions 1 and 4 would run together, and then instructions 2 and 5 would run together, and then this program would be complete. And so it would all be over in 3 cycles, which is great. Independently, there is a separate process at the end of this pipeline that's looking at the top of this table and is looking for the first one that is complete. So, when this one is actually finished over here, retirement says, okay, this one is now finished. It got the value 9 or whatever it got, and it wanted to write to A. And so now finally, this is the only actual time that the real A register, which does exist somewhere on the chip, is updated with the value 9 in the order that the program actually completed things in.
Right.
And so this retirement stage kind of...
almost a collapse, is it, like collapsing it all down back into what? Yeah.
Exactly. So all this stuff could have happened in any which order we liked, provided the answer was correct. And we know that if we followed the routine of like, well, this thing had to happen after this thing, then the answers will be right. But from a programmer's point of view, viewing it from the outside, or from anyone who's on the outside of the CPU looking at what happens with memory, then it's as if it happened in sequence. It just happened really quickly, which is cool. And that also plugs into that whole branch prediction thing, because, for example, if one of these was a branch and we got it wrong, we just wipe the table from here down and go, let's pretend none of this ever happened. Now, I think anyone who's watched these videos has a decent understanding about how modern CPUs work from the internals, microarchitecture, this is called. Mm-hmm. We didn't really talk, there's some things that are perhaps honorable mentions we can go into, which is... so the way that I think about it again is like the robot at the front of the thing that's shoveling in chunks. It's typically much more efficient to grab large swathes, large being like, say, 64 bytes or 16 bytes of memory at a time, which could be multiple instructions. And so that robot is potentially picking up anywhere to tens of instructions at a time. And then behind that robot, there is a sort of second thing, which is like, well, where are the instructions in this block of numbers? Because it's just a big block of numbers. And it's not necessarily straightforward to determine how many numbers you need to read for which kinds of instructions. So on x86 CPUs, the instructions are variable lengths. Some instructions are 1 byte long, some instructions are 4 bytes long, some of them are 15 bytes long, some of them have weird prefixes that says, hey, this changes the meaning of the next block of bytes. And that's really complicated. And so there's a set of set of stages along the pipeline where someone's picking over those bytes and trying to work out where the instructions actually lie in those groups of numbers, and kind of putting tags around them to say, well, this is one instruction, this is another instruction. And then finally they get to a stage where those instructions are actually broken down into sub instructions. They're called micro operations. So for example, let's look at this. And again, this is a 6502. It doesn't really do this, but it gives us some idea. This load A 100, X, I sort of glossed over a little bit. We talked about it earlier. This X means index the address 100 with the X register, which says, where we are relative to some fixed points. But what it effectively means really is that this instruction, which just says read from this memory location, the first thing I have to do is I have to take the X register and add 100 to it to work out which slot I need to go and read from. And then I need to go and read from that slot. So it's really two pieces of work hiding in one instruction. And most CPUs will actually break those down into separate pieces because maybe the load store unit that's reading and writing to memory is really busy, but there's nothing to stop you from working out where the address should be done. So you might want to break it into 2 pieces and get that started early. And so that table that we drew out on the whiteboard, that really should have been done in terms of micro operations, these tiny little pieces, which, especially on Intel processors, there can be like dozens of those things. Some of those instructions are very complicated. On the other hand, the ARM processor that's in everyone's pocket right now has fixed sized instructions. They were very carefully designed so that all the instructions they wanted to do would always be either 2 bytes or 4 bytes long. And those are a little bit simpler. So you normally need more instructions to do the same amount of work, but they don't need to be broken into these micro operations in quite the same way. So there's some examples of how CPUs have taken different approaches. And in the sort of 70s and 80s, there was this big furore about CISC versus RISC, which was reduced instruction set computers versus complex instruction set computers, where ARM was very much on the RISC side of things and Intel remains on the CISC side of things. Now, in some ways, like politics, everyone's kind of ended up in the middle somewhere. Actually, maybe that's not so true anymore with politics, but that's a whole different conversation.
Well, I was tempted to quote from the film Hackers, but I decided not to.
That was very restrained of you. What was the quote?
RISC processing, man, it's going to change everything, I think is the... Slightly paraphrased, but along the lines of, yeah.
RISC architecture is going to change everything.
Yeah, RISC is good.
I think it's when Apple went down the Motorola route and they were looking at this laptop that had a motor. Am I remembering that right? Because that's kind of like
I'm embarrassed to say I don't think I've ever seen the film.
Well, it's a guilty pleasure. It's a lot of fun. It's worth a watch. Anyway,
okay, maybe that'll be this evening's entertainment on my side. I can try and that would be fun. So yeah, we've pretty much got to the end, and one thing I've really glossed over is talking about that memory. Memory is a lot more complicated than I've made it sound with our little pigeonhole boxes, which again, most viewers don't even know what a pigeonhole is. It's a died concept from like universities in the 80s and 90s. But we'll talk about that maybe another time.
It looks at the page number and there'll be a table somewhere in the computer, usually in memory, that is accessed at a fixed location. So it'll look up 8 in here and it will say here that all these exist at location, let's say